Hello physical science students, and now that you know a little bit about light, we're going to look at how light is produced and used. We are going to look at different kinds of lighting: incandescent, fluorescent lighting, neon lights, sodium vapor and tungsten halogen lights, and lasers. We're also going to look how light is used in lasers, polarized light, holography, optical fibers, and optical scanners. Incandescent light is a very common kind of lighting. A lot of the light bulbs in your house are probably incandescent bulbs. And incandescent light is generated by heating a piece of metal until it glows. The metal is usually made out of the element tungsten, and we call it a filament. And it is shaped in a coil shape, and when an electric current passes through that filament, the electric resistance of that metal causes the filament to become hot enough to give off light. Incandescent bulbs are very inefficient because about 90% of the energy given off by the bulb is in the form of thermal energy instead of light. Fluorescent lighting is produced in a little bit different way. It generates light by using phosphors, spelled with a PH here, to convert ultraviolet radiation into visible light. A phosphor is a substance that absorbs UV radiation and then emits visible light. And the fluorescent tubing is coated with, the inside of that is coated with phosphors. And in fluorescent lighting, we usually have two electrodes which are connected via a circuit. And when the light is on, these electrodes emit electrons, and those electrons collide with the gas in this tube. There's different kinds of gas which emit ultraviolet radiation. The wavelength of the light depends on the kind of the gas that is used, because different gases will emit different wavelengths. The phosphors then absorb the ultraviolet radiation and convert it into visible light. Fluorescent lights are far more efficient than incandescent lights because they don't use so much of their electrical energy heating up a filament that is basically warming the air around it and giving off a little bit of light. Instead, fluorescent lights are able to convert a lot more of that electrical energy into producing light instead of to producing thermal energy that warms the air around them. You've all seen examples of neon lights and signs. Neon lights work in a similar way to fluorescent lights. They're a tube filled with gas, and when an electric current runs through the tube, the electrons collide with those gas molecules, but in this case, the gas molecules actually emit visible light. Neon, if the gas is neon, the light is usually a bright red-orange color. If you see other colors besides the bright orange-red, those are different gases that are being used to make those colors. Here are two other types of lighting. One, sodium vapor lights. They're often used in street lights or outdoor lighting, and they basically are a tube that contains a mixture of neon gas and argon gas in small amounts and a sodium metal. And when the lamp is turned on, the gas becomes very hot, enough so that that sodium metal starts to turn to vapor and it emits a yellow-orange glow. The other kind of light on this page, tungsten halogen lights. They are named that because they have a tungsten filament, kind of like incandescent lights, but inside of the bulb is a halogen, and examples of a halogen gas would be fluorine or chlorine, and that gas enables the tungsten filament to get much hotter than ordinary. So these lights are very, very bright. They're oftentimes used as car headlights, or for underwater photography lighting will use tungsten halogen bulbs. Also, the interaction between the halogen, the fluorine or chlorine gas, and the tungsten metals enables this light to last much, much, much longer than a typical incandescent bulb. Now let's take a look at producing light in the form of lasers. The word laser comes from light amplification by stimulated emission of radiation. And lasers can be made with many different kinds of materials. They can be made with gases, liquids, or solids. The wavelength of the laser depends on what kinds of materials are used. A very common laser is the helium neon laser. But let's look at what happens in a laser and why what that type of light is and how it's produced. In a helium neon laser, a mixture of helium and neon gases is contained in a sealed tube, and that sealed tube has mirrors at both ends of the tube. The atoms inside here absorb radiant energy from a device that produces short, bright flashes of light. When those atoms absorb the energy, then they release the excess energy by emitting light waves of a particular wavelength. And here these are emitting light waves of particular wavelengths. Those are emitted in all different directions, just randomly. But the ones traveling along the tube are reflected between the two mirrors. And as they travel, the light waves stimulate other atoms to emit more light waves. And the result is an increase in the amount of light waves traveling back and forth along the tube. The light waves begin to line up as they bounce back and forth between the two mirrors, and we see a laser because one of those mirrors, in this diagram, this is called the semi-reflecting mirror, or it's only partially reflecting. So a narrow, intense laser beam can be emitted from that partially reflective end of the tube, and that illustrates how a laser beam of light is created. You can see that this type of light in lasers is a special kind of light, and it has a special kind of name. It's called coherent light, and it's very different from incoherent light. Incoherent light would be ordinary light, or light that maybe comes off of an incandescent bulb or a fluorescent bulb or even a neon tube. It has more than one wavelength, more than one direction. These wavelengths are all different and they're going in all different directions, and their crests are not at constant distances. They are not aligned by each other in any way, shape, or form. Laser light, on the other hand, is coherent light, and coherent light is light that has one wavelength, it travels in one direction, and there is a constant distance between the corresponding crests. You can see these are coherent because all three of those factors are true about coherent light. Because lasers use coherent light, a laser beam does not spread out as it travels over long distances, and so it can apply a lot of energy to very small areas. There are a lot of applications for lasers. Powerful lasers are used for cutting and welding materials. Surveyors and builders use lasers for measuring distances or leveling. In communications, information can be recorded in pulses of light from lasers. In medicine, surgeons can use lasers in place of scalpels to cut through body tissue. So they're often used to remove cataracts, reshape corneas, repair retinas, remove small tumors in the body or birthmarks. CDs and video discs are items that use a lot of lasers. When CDs are produced, when the disc is produced, the information is burned into this reflective surface with a laser. The laser creates millions of tiny little pits, and these are magnified to a great degree, and those patterns start at the center of the disc and move spirally outward toward the edge. When that CD is read, a laser beam strikes a pit, one of these little pits or flat spots, and different amounts of light are reflected to a light sensor, and that reflected light is converted to an electrical signal that can be converted into a sound or an image. Optical scanners are another example of usefulness for lasers. In this case, lasers read the barcodes. Let's look at another way that we use light, and that is with polarizing filters and polarized lenses. What is polarized light anyway? Remember that light is a transverse wave, and it can vibrate in any direction. The direction of vibration for a light wave refers to the direction that its electric or magnetic field vibrates. Linearly polarized light is light with a magnetic field that vibrates in only one direction. Light can be polarized by using a special filter with lines of crystals that act like a group of parallel slits, kind of like the slits on a picket fence. Only light waves with magnetic fields that vibrate in the same direction as the lines of these crystals can pass through. Polarized lenses, like sunglasses, use these polarizing filters in a particular way. Let's say that light is being reflected from a horizontal surface, like a lake. Some of that is polarized with its magnetic field vibrating vertically. The lenses, if we put two polarizing filters together to make a polarized lens, they will block some of that reflected light because they are at right angles to each other. So these sunglasses with these polarizing filters block the reflected light with vertically vibrating magnetic fields and reduce the glare. Another way that we use light is in holography. Holography is just a technique that produces a hologram, which is a complete three-dimensional image. Lasers are used to produce holograms. Holograms are used on legal documents for security reasons, on credit cards, also in art, and for fun. Now let's take a look at optical fibers. And to understand what is happening in optical fibers, we need to talk a little bit more about reflection and refraction. Let's look at light traveling from one medium to another. Let's just for ease of doing this, let's say this is water and this is air, and light is being shined through this water and traveling then into another medium. Some of that light will be refracted. This is refraction, the bending of light as it travels from one medium to another. Some will be reflected, and it will actually reflect off of that surface and back into that same medium. If we change the angle that we are shining this light and we make it at a larger angle, we will see that the refracted light will bend closer to the surface of the water, and we will also find that we will get more and more reflected light. As we increase the angle even more, we see this happening even more. This is closer to the surface until at a certain angle, we call it the critical angle because the refracted ray has been bent so much that it is actually traveling along the surface of the water. For a light ray traveling from water into air, the critical angle is about 49 degrees. Now, what happens if we continue to increase that angle and we go greater than 49 degrees, greater than the critical angle? At that point, when we increase that angle even more, we will get no refraction, but only reflection. And that is called total internal reflection. It occurs at angles that are greater than the critical angle. Optical fibers actually use this idea of total internal reflection. The light moves like water through a pipe. Total internal reflection is possible because the core of the fiber in optical fibers are made with glass from two different indices of refraction, and that is what makes optical fibers work and makes that possible. They're used most often in communications, but they also have a lot of medical uses as well. Advanced, here's some ideas, but certainly if you have some questions, you want to look a little bit more into optical fibers and their uses and how that works, into holography, into any of the things that we've talked about. Do a little research, come in, show me what you find, and I look forward to seeing you in class.